name is Radha Bahukutumbi, and I'm a distinguished scientist at the Laboratory for Laser Energetics at the University of Rochester. I study plasmas, which are highly ionized material that's produced by lasers. I'm interested in this because it has many applications. It has the potential to produce energy, which might really change our energy landscape because this would be clean, sustainable baseload power. And also, it creates materials that you can study that might be at the interiors of planets like Jupiter and so on. So inertial confinement fusion, as the name suggests, there is inertia, and there is confinement, and there is fusion. You have lasers which are incident on this capsule containing a layer of frozen deuterium and tritium. And as you drive this capsule in, it literally implodes like a rocket. So these alpha particles that are then produced can then move through the target, redepositing their energy. And once they redeposit their energy, they raise the temperature of the target, which in turn can induce more fusion reactions to take place. So inertial confinement fusion is very interesting because it has the potential to produce useful energy out of an implosion. It's also very interesting because the kinds of conditions that we produce in these kinds of implosions are very high density, like those at the interiors of planets like Jupiter. So you can study the properties of matter under those conditions and try to understand what's happening in the core of such planets. Radiation hydrodynamics codes are numerical codes that basically model an inertial confinement fusion implosion. So the typical physics they include are the laser deposition models, they include heat conduction, they include radiation and how it's transported throughout the target. They include fusion reaction cross-sections. They also include what's called an equation of state. One does modeling for several reasons. You have to prove this concept of inertial confinement fusion as a source to study the interiors of planets or as an energy source. So to design an experiment, you actually have to have some prediction or scope out some parameter space. What size of a target do you want? What sort of a driver do you want? What can you observe that tells you that your model is right? So in order to make those predictions, you need validated models based on experiments that we can do today. And that's the big idea behind modeling. This field is really taking off both within the US and internationally. There is a lot of interesting problems that one could solve, not only in terms of trying to understand the physics of matter at these conditions. There's a lot of machine learning opportunities that could be applied to this field. There's a lot of computational aspects with exascale computing coming around the corner. So the opportunities are plenty and very varied, all with the basis of trying to understand the properties of this material that we generate and manipulate it in some controllable way. In research, you start out by really not knowing what the right answer is. And that's actually true of life too. So research sort of mimics life, I would say. What you start out with is a question that you really want to answer. And what you need is the determination and the persistence to go through to answer that question. You may make many mistakes along the way. That's okay. You have to learn from those and learn to ask the next question so that you can continue moving on towards the goal that you have, which is the first question that you asked yourself.